All right, welcome everybody. It's very nice to be here. We're going to be giving a talk today about Rust, Kubernetes, and the cloud. But before we get started, who are we? Well, I'm Ryan Levick. I'm a cloud developer advocate at Microsoft, and I spend all my days and weekends and nights thinking and dreaming about the Rust programming language.
Hi, everyone. I'm Taylor Thomas. I am also a developer at Microsoft. I'm working more in the cloud side, the cloud native, as we like to call it in buzzword language. I work more on that side. I do more than a little bit than dream in Rust, and that is no knock against Ryan because Ryan is quite good at Rust. But I do a lot of things with Kubernetes and have for a while, and basically a lot of my career's been in the cloud space. So that's kind of my background.
So we're talking about the Rust programming language today. Maybe you've heard of it before, but today we're going to be talking about how Rust has come to find a home at Microsoft, how we think about Rust at Microsoft, and sort of where Rust fits in the cloud space today. And to begin with that, we're going to talk about Microsoft's problem, our problem. And it's not just our problem, it's really our all problem. It's a problem that the software industry in general has. And that is the fact that our systems are more interconnected and performing more and more tasks every single day. But along with that, what that means is that our systems are more vulnerable and attackers have more incentive to attack us. And so you might be thinking, okay, what does that have to do with Rust? Well, if we look at over time the number of CVEs, that's the most secure security, or the most serious security vulnerabilities over time, you can see that the number is just going up. This stops at 2018, but over the past 3 years, it's basically been the same story. It's going up and up and up. Fortunately, we see a little bit less of those vulnerabilities being actually exploited in practice, but that's not out of magic or anything like that. That's just out of spending a lot of money on the problem, basically by hiring great security engineers and by paying a lot of money in bug bounties and things like that, so that there's less incentive to exploit it. But that costs us, Microsoft, and us, the industry, a lot of time, a lot of effort, a lot of money, and it's just a lot of headache. How much does this cost exactly in kind of dollar figures? Well, here is a figure, $150,000, and you might think, oh, that's not a lot. Well, this figure is about 20 years old. It's unfortunately the latest figure that we have. It's from around 2002, I think. And that's per CVE that we have. And it's basically just the cost of addressing the CVE directly. It does not take into account the headache that the customer had to go through, support costs, shipping new code out. It's really just addressing the bug itself that happens in production. So this figure is probably much larger nowadays because our systems are much more complex. And how many of these do we have every year? This figure is a little bit more recent, but I think this was 2019. We had 468 of them. And so if you just think that we're spending just on addressing the issue directly in the tens of millions of dollars and 2002 dollar figures, that's a lot of money. And that, again, does not take into account all the headache that comes with it, the cost to the customer of actually shipping patches and things like that. So it's really quite a big deal. And really at the core of this problem, at the core of our problem as a software industry, is the fact of memory safety, or rather memory unsafety. The fact that a lot of these security vulnerabilities come from exploiting the incorrect use of memory. And if you look at the percentage of these very severe security vulnerabilities, about 70% of them are due to memory safety issues, so the incorrect use of memory safety. And then 30% of them don't have to do with that. They're kind of logic bugs or something like that. So it kind of stands to reason, if we can address this memory safety issue, the incorrect use of memory, then presumably 70% of our worst security vulnerabilities will just disappear. And that would be fantastic. Wouldn't mean that our systems are magically completely secure, but 70% going away means we can focus our time and attention on that 30% and really try and hone in on those, which would be a fantastic thing. Is Rust the answer to this? You may not know this, but Rust is a systems programming language that is 100% memory safe. And so if you don't have if you use Rust, then you don't have the issue of memory safety because Rust is 100% safe. It is a language that kind of addresses this problem at the core. If you use safe Rust, then you can be sure that your systems are 100% safe. And along with this, you're not kind of sacrificing performance that you would have. Now, memory safety is typically in the realm of when you're using languages like C and C++, you might be thinking to yourself, I'm a C# developer or Java or JavaScript or whatever you're using, and we don't have these memory safety issues. That might be true for your particular applications, but I still implore you to think about this because you're running on top of system software, the software that you rely on, like your database, your operating system, all the tools that come around with it, usually are written in these memory unsafe languages like C and C++. And with Rust, we can replace those languages and still keep the reason that we use those languages in the first place, which is usually performance and control. On top of that, and related to memory safety, is the idea of correctness. So when we use Rust, we get a lot of features in the language that are there in order to make sure that the programs that we're writing are correct, that we don't have bugs in them. Now, it's totally possible to write bugs in Rust. Taylor and I, we have both written our fair share of bugs in Rust. But one thing that's kind of hard to quantify is that when you do write Rust code, you tend to write code that is less buggy than in other languages. And that includes languages with garbage collectors like C# or Java. So this is we don't have kind of numbers to really concretely say how much this is true, but it is certainly something that we're finding anecdotally to be true. And along with that, you can become highly productive in this language. If you've heard anything about Rust before, you've probably heard that it has a steep learning curve, that it's not the easiest language in the world to learn, and that can certainly be true. But it's definitely not the hardest one to learn. If you've ever learned to use C or C++ correctly in a way where you do not have bugs and incorrect use of memory, that oftentimes takes years of training. And in Rust, that typically lasts 3 or 4 weeks of learning. And once you reach that level, the productivity really takes off, and you can write systems that are correct, that do what they need to do, are relatively bug-free, in a time frame that's much faster than you potentially would in other languages, which is fantastic. And then above all else, you can tell I'm a big fan of Rust. You might be thinking this guy up here on my screen is just spouting the Rust gospel, but I don't he's just one person. But I'm not alone. Stack Overflow submits their yearly survey for developers, and Rust for the past 5 years has been #1 on that list. So it seems to be that other people also enjoy this language. So even if you don't think Rust is right for you, it could be a fun language to learn, and it is at times a joy to use. Really at the core of this is that Rust, that we want to reduce the use of memory unsafe languages like C and C++ through the use of Rust. The fact of the matter is that C and C++ are here to stay. They're not going to go anywhere anytime soon. There's just far too much software written in them. I'm not proposing that we completely stop writing C++ or that we just rewrite everything in Rust, because that's just simply impractical. Even if I wanted that to be true, it would be far too costly and take far too long for that to ever actually be true. So it's really about reducing our dependence on these memory unsafe languages, and instead relying on a safe language for the most critical systems that we have.
And this raises the question for a lot of people, I'm assuming in this audience, you're like, but wait, I'm using C#, or but what if I'm using this memory safe language? So that's a really good question. And that's something I want to address because, like I said, my experience is coming from those in the cloud world, coming from those, that background of memory safe languages, whether that's doing something like Go, which is my original background. You have this is the Go Gopher, in case you're not sure. Rust is a crab because we're Rustaceans, and Go's are Go programmers are gophers. And so this is the Go mascot. And a lot of people who do things, especially with Kubernetes, do things with Go. And people always say, but wait, my language is already memory safe. And so I wanted to address that a little bit, but in context of a project that we have called Krustlet. Krustlet is we're going to talk a lot about it. I'm going to show a lot of demos around it. We're going to get into the demo thing. We want to kind of explain why we're even talking about Rust here in this in this conference. Like, well, why Rust? What does this have to do with Azure? Well, that's what we're getting into here. So Krustlet is a project we started that is essentially a Kubernetes kubelet, which, if you are not familiar with Kubernetes, is the node aspect. So it's what runs on every node in a cluster of Kubernetes nodes, and that thing connects it to the main API and registers it and does all of those tasks. And so we wrote a kubelet in Rust. And for what crazy purpose, you might ask? That's actually for webassembly, or WASM, which you saw was also one of the most loved languages on there. That's just a little aside. But we are doing a lot of things with webassembly, which is somewhere where we see the cloud moving towards here in the near future, just because of its ability to run on multiple systems, have a lot smaller footprint than normal containers. But Krustlet allows you to try it in something that's somewhat familiar. If you're new to cloud, you've probably at least heard of Kubernetes. And if you've been in the cloud for a while or are in the process of moving over, you have probably touched it in some way. And so Krustlet allows you to just basically load it, and we'll show that today, load it straight into something like AKS, and then go and just run WebAssembly modules, which are the binaries that are generated from WebAssembly. So before we talk about that, I just want to say that's kind of the context that I'll show some of these demos in here. But why did we choose Rust over a memory-safe language like Go? So the first point that I always like to point out is traits. If in the Rust system, there is a concept called traits. And if you are familiar with most other languages, they're called interfaces in other languages, but they're kind of a step above. Traits allow you to express basically the desired behavior like an interface would, but you can use those traits as bounds inside of your functions for generics. But more importantly, there's things such as what we like to call the conversion traits. These, if you've experimented with Rust at all, you've probably seen asref. There's things like asref, dref, whole bunch of them, and all of these traits allow you to actually convert types over or use a type as another type in a very, very safe and generic way. They're just very flexible and powerful, and we'll kind of go over some examples of that in a little bit. Next up is macros. So macros are a common thing in many languages, but Rust macros are beautiful. That'll probably be the first example I show. There's a few things, like I try to always keep it real for everybody as we talk about these things. Like I don't want to come off as a fanboy, but macros is one of the things I will gush about. It makes code so nice to write, and particularly in a cloud environment, just because you're interacting with so many APIs and so many different things, where the combination of something that has traits that you can then reuse a bunch of code with ease, and then the macros allow you to generate code without having to store a bunch of weird things, like what happens with Go and Kubernetes. And we'll show some examples of that in a little bit. The next thing we really love is the error handling and iteration tools. So if you're familiar with link style program or anything from the functional programming world, a lot of that is available in Rust. And it goes together with the error handling, because error handling is their values, but they're values that have to be handled or they raise a compiler warning. And the tools for handling those errors are really, really nice. You're able to map one, like a type, into another type, or if it is an error, do something all with relative ease. And then you have the iteration tools as well that allow you to go into filtering and mapping and collecting. You can basically do an example of filtering or putting out a bunch of asynchronous tasks, basically a fan out, fan in job in a very, very short amount of code. We're talking 10, 15 lines. And that's really, really incredible for a language. And especially when you do a lot of things like that with data massaging and things in cloud computing. And last, or not last, but one of the other things we really like is dependency management tooling. Now, dependency management is a hard problem to solve in general, but the dependency management and build toolchain for Rust, which is called Cargo, is very, very powerful and very useful. I have fought a lot in languages like Go that are just a nightmare to upgrade any dependent, because you have to get the right SHAs and do all these things. And even with ones that are a little bit more fully featured, you still have a lot of problems with dependency resolution. And what if I want to try out something locally or patch something? And Cargo makes that very, very easy for you. It is just, that's one of the other things I will gush about is Cargo, just because it is so powerful and useful. And that's why those are some of the big reasons we chose like Rust over something like Go. And last off is that mentioning of correctness. So memory safety, obviously, like we mentioned, like things like Go and Java and C# are memory safe. They're meant to be memory safe, but they're not necessarily correct in their usage of things. So a quick example of this from the Kubernetes world. So I actually just recently stepped down as a core maintainer of the Helm project, but I worked on that for a long time. Once again, if you are familiar with Kubernetes, you've probably heard of Helm, which is a package manager for Kubernetes. And we've discovered over the years several bugs that were race conditions not detected by the race checker in Go or anything. And that bug actually would have been completely impossible in Rust, because it has caught us. What generally happens as you're learning Rust is you see something, you're like, no, this is right. And the compiler's telling you, no, you're wrong. And you're like, no, but I am right. And then you like sit there and you look through it and you dig through, you're like, oh, I'm accessing that data when I don't have actually, like something else could be accessing it simultaneously, or I don't have the correct ownership over it. And so that correctness is very, very important to us as we've been coding things for the cloud. So this also brings up the other question: why not Rust for the cloud? Like, when's reasons you should or shouldn't use Rust for the cloud? So let's talk about that. The first thing is the async environment. So async was something that was added a little bit later in Rust's development. It's still technically very new. It's about a year and a half old in terms of being in the stable branch. And it has some rough edges still. Now, that's not to say that it's impossible or overly difficult, but there's currently lots of work being done here. There's a work group that was started that's gathering different requirements and things from community members to make the async story better. But it is, if you're used to something like Go in particular, where you can just say go run something, like just go do a function, you're going to have a lot of rough edges to get used to. But like I said, there's a correctness benefit that comes from using async with Rust. Another thing is that the ecosystem can sometimes be immature for cloud usage. A quick example here is we were trying to do something like parsing a multi-part data from an HTTP request. Turns out basically all the libraries only support multi-part form. And so if you're trying to send any other kinds of data, now that's something like really simple and really small, might only affect some projects, but you'll find lots of gaps like that because people haven't really used all of it in the cloud until recently, in my opinion, at least. And so just be aware that the ecosystem is a little immature sometimes in that area. Now, like Ryan mentioned, there is a learning curve to Rust. And it really is just the initial learning curve. I like to call it logarithmic. And don't take that in like an extreme way. It's just that's what the curve looks like. You kind of have this initial period of where it's just a very sharp curve as you kind of have to learn things about like the borrow checker and ownership in Rust and how all those things function. But really, this comes into play when you're trying to do something quickly. If you want to throw a team onto a new project in Go, they'll be able to, and a small project in Go, they will get it done quicker if they've never done Go compared to if they've never done Rust. But like I said, it's only a small curve, and the benefits, you're back to normal productivity after about 3 or 4 weeks.
All right. So I think now we're going to be going to a demo to show off what Rust code looks like. Well, this is a very short presentation, and so we're not going to be able to show what how Rust works. This is not a Rust 101 course or something like that. This is really meant to be kind of an overview of what you might experience if you use Rust. So don't worry if you don't understand every line. If you haven't done Rust before, you certainly won't. But this should just give you a flavor of what that kind of looks like. All right, so I'm sharing my screen here now, and hopefully you should be able to see what I have going on here. And this is a simple project that I've started. And what you're looking at right here is the cargo.toml file for my project. This is a Rust project. Cargo is Rust's build tool / dependency manager / test runner, kind of does everything around building and testing and running Rust. And this is sort of a manifest file describing some metadata about my project, like the name, the version, who the author was, and things like that. And then down here, this is kind of one of the best parts about Rust, is the dependency management is quite simple. So I'm going to be using two of our libraries from Azure here. One is Azure Core. The other one is Azure Cosmos, because we're going to be writing a small little demo with Cosmos DB. Then I'm going to be using Tokio, which Tokio is an async runtime. Now, Rust, because it's a systems programming language, doesn't have a runtime built into it like JavaScript does or C# does. You have to provide the runtime for you. What's really great about that is that you can switch runtimes out depending on your use case. So if you need something that runs on a Raspberry Pi, that might be very different than something that runs on a beefy server in Azure. And this allows you to kind of switch them out to use which one you want to use. And then request here is a simple HTTP library that runs on top of Tokio that we're going to be using to actually power the HTTP requests that we make to Azure here. And then I'm going to pop on over here to our main.rs file. This is kind of everything that we have so far in our little app that we have going here. You can see that we have a main function that's going to be run automatically when we run our binary. And it's annotated with this funky thing here called Tokio main. And that's because normally main functions, just like in C, are not asynchronous. But this little Tokio main annotation here allows you to make your main function asynchronous, and it builds a Tokio runtime for you and runs your main function on that runtime. So it's there's a lot going on here underneath the hood, but you get very nice, short, concise annotations that help you build up your application. This is an example of what Taylor was talking about with macros. This Tokio main here is a macro that is generating some code for running our code on a Tokio runtime. The code is quite simple for what it does. We're going to pass in a Cosmos primary key, the name of our Cosmos account here. We're going to get an authorization token based on our primary key. We're going to build up here an HTTP client that actually will power our HTTP requests. This is because our Cosmos client, all the Azure SDK clients that we are building right now, are agnostic to what underlying HTTP library that they use. So you can plug in your favorite HTTP library, and that's what will be used by the various libraries that we're building for Azure. Now, I just want to mention one other thing about the Azure SDK that we're using here today. I'm going to pop back over here. You may notice that I'm getting these dependencies from GitHub, whereas these other ones, I'm just specifying their versions. That's because these two, Tokio and requests, are coming from the centralized Rust library store. The libraries in Rust are called crates. This is coming from crates.io, which is something that you can think of like NPM or some kind of package store that you might use. We do not yet publish these on crates.io. Our Azure SDKs are not currently on crates.io because they're under heavy construction right now. It was a community project and has been moved onto the Azure organization as a alpha, unsupported, unofficial SDK. So while we do have Microsoft people working on it full time, I work on it quite often, as does Taylor. It's not yet to the point yet where we can provide official support, where you can call somebody up and have them help you with it. But we hope to one day get to that point. It doesn't necessarily mean that it's bad software or anything like that. It's just when we say it's an officially supported SDK, that's a very, very high standard that we're not quite ready to grant the Azure SDK for Rust quite yet. So what I want to go ahead and do here real quick is try and show how to make a request to Cosmos DB using our Cosmos client to just fetch the various databases that I have inside of my Cosmos DB account that I have here. So if we type out Cosmos client here, and you can see there's a whole bunch of methods that come with this, and I can call list databases here, and then I can call execute, because list databases just gives us back a request object that we can add some additional optional features to, and then we're going to call execute on it, and then await on the result of calling execute, and then we can store that into a variable that I'll call response here. You'll notice I didn't type this result thing right here. This is not me typing it, but this is Rust's Rust Analyzer plugin extension for VS Code that gives some very nice additional information about our Rust code. So it's telling me the type here. And the result type here is just saying that this operation might fail. It might error out. And error handling in Rust is real nice and easy. All you have to do is add a question mark here, and it basically pops the error out from the main function and returns an error if our call to execute errors here. Pretty plain and simple. And then in order to get the names of our databases that we have here, we can go ahead and do something like we'll call print line here. And then I'm just going to say the databases are going to be the response.databases. And we have to, call .iter here, and then map, and we get each database in turn, and then we can call db .name. That gets the name of the database, and then we collect all of these together. Oops, and I'm in the wrong place here. We collect all of these into a vector, which is basically like an array of string objects, just like this. So if you've not done Rust before, you might be confused at some of the syntax and stuff like that. That's part of learning Rust. But this hopefully should work. And I'm just going to pop up this here. This is a terminal right here, and I'm going to go ahead and run cargo run, which will build and run my executable, and we'll see what it says. I've already set the Cosmos primary key and Cosmos account in my environment, and it should hopefully work out just fine. And there we go. So I do have one database in my account. It's the test1 database, and we have been successfully able to use the Azure SDK for Rust in its current form in order to fetch that from my Cosmos account. So nothing new here. You probably are already doing this with your SDKs in your current language, but it goes to show that Rust, being a systems language, doesn't mean that it's a huge verbose monster. We actually have a lot of high-level kind of link style, functional programming style, very modern error handling that you can use in the systems database, and we don't even rely on a garbage collector in order to get it done. And with that, I'm going to stop sharing my screen, and we're going to head over to Taylor for his demo.
Yep. And so just while I'm starting my my screen share, I just wanted to point out like that. I love how simple we're able to go and iterate over. Like that's one of those things is if you're in the cloud world, you're basically going to be like mashing data around and doing things, but you were able to quickly pull in all the information from that project, and then just iterate across it and mash all the stuff together just all in one quick. I mean, that entire thing was, when you formatted it, like 8 lines. When you didn't have it formatted, it was 2 lines. And so that's just, you're combining all these awesome correctness guarantees we've talked about with the mapping function. So we just wanted to point out to people, because people here are interested in and using Azure, that you can start using these things. Yes, some of these things are under construction, like the SDK. But if you're interested in doing it and you want to interact with the Azure APIs, there are tools there that you can, even at this point, if you were to start using them in the next few months, be able to give us important feedback and say, hey, I found this bug, I need this feature, why doesn't it do this? Or, oh, I really like this, can you make the other things do it like this? Or whatever you want to do. So just something good to point out from that code. So here, I just wanted to actually first and foremost share some things about Krustlet. So now we're going to go into the Kubernetes portion of this. We talked a little bit about Azure. Now we're going to talk about Kubernetes, Azure, and Rust all together. Right here is the Krustlet project. You can find it on Deus Labs Krustlet on GitHub. But before I start with kind of showing some of the cool things that Rust can do for you, I'm going to first start off basically adding Krustlet to an AKS cluster for you. So we have something that walks you through how to do this. Inside the docs folder, you actually can see various examples. Inside our how-to, we have it for pretty much every kind of major cloud provider. But here on Azure, you'll see that it has a very, very quick guide. So the first thing you'll need to do is create a service principal, which I've already done. And then make sure you have an SSH key. But then you have this deploy to Azure button. So I'm going to move over here where I already clicked on that. And I'm going to create a new resource group called, I'm just going to call it Krusty, because Krusty the Crab and also Krustlet. And then I'll just put this, I like to put things, actually, since we're doing it in Europe, I will find a area over in the EU. Let's do West Europe. And then basically all the things are all set up for you. You can even specify your Kubernetes version. I'm actually going to specify we recently released a newer version of Krustlet, 0.7. So I'm going to change it to make sure it downloads that. And that's it. All I have to do is then do the review and create, let it validate the template. Oh, it looks like it failed. Let's see what I did. Because, of course, I am angering the demo gods. Oh, I might not have permission. So here, I'm going to switch up this to here, and we'll do it in West Europe. Okay. So we'll go ahead and create this now, and in the background, I'll let it run while I run through some of my examples. So this is, if you are familiar with Azure, which I'm imagining almost all of you are, this is very simple, just following your normal kind of Azure deployment template framework. So we're going to go ahead and do that, and then we'll show some things here inside of code. So I wanted to show a little bit more on Rust and then show how we're using Krustlet with some actual demos of this. But the first example, and probably the most important example I want to show you, is how macros can do some really interesting and cool things for you. So I'm going to go over to a project called Crater. This is a crate we released that allows you to write Kubernetes operators in Rust. And so if that's something that interests you, this is probably a good place to start, because our kubelet is actually built on this crate that we've created. So this actually, we're hoping to make something that's completely separate from the Krustlet project in the future. But there's a great example in here that shows how you can use macros and things to your advantage. So inside of Kubernetes, this is a part where we're getting to a little bit of prior Kubernetes knowledge. I'm going to explain a little bit, but if anyone has any questions, please feel free to drop those in chat or in Discord, and I can answer those. But inside of Kubernetes, you have Kubernetes resources, and all of them kind of have a similar look to each other. They have a very common set of parameters that are set with them. But there's also a type of resource in Kubernetes called a custom resource, or a CRD. And that stands for custom resource definition. This allows you to basically add on arbitrary APIs to the Kubernetes API. And then it starts handling them like normal Kubernetes objects. And then you can write controllers or pieces of software that can handle those objects and do things for you. So people do this to set up things like various clusters that need to be orchestrated. So like database clusters are a common thing you'll see. Also to set up custom resources for your company. That's also quite common. So this one is a funny one that uses Moose as the example, but we have this custom resource derived that's going on. So these are all macros here at this top level, and let's kind of walk through what this is all doing for you. So if you're used to doing this, probably in Go, you might have also done it in Python or another language, but you have to generate a lot of code. So you have to create your object, and then you have to generate the code for that object that creates the client for it and the handling for it. And then in Go, at least, you have to commit that code. I don't know if other languages have to, but either way, there's still a bunch of code generation that has to go on. So instead of having like an out-of-band generation step or these things that happen with other languages, we have just this custom resource derive. And this does a whole bunch of magic that creates all of that client stuff for you when you build the project. So this doesn't clog up your code base with all this other kind of just scaffolding glue code that's in there. These other things such as serialize and deserialize, these derive an implementation for a powerful library in Rust called SERDI, which stands for serialize, deserialize. And basically any data model that has an implementation, so we're talking TOML, YAML, JSON, message pack, any of those things can now serialize or deserialize these objects into their specific message format. So there's no extra like attaching it on. It's just you derive those two things. And then this also has the bonus of adding on a JSON schema. So for those of us who consume a lot of APIs, there's often these schemas that we need to use to apply or check or validate things as they come in. And once again, I do almost no work and get a full JSON schema validation for this type by basically specifying this derive and then specifying a few attributes for in this case, the custom resource. And so this does all the heavy lifting for me to generate those things. So in Go, which is, like I said, the one I'm most familiar with, this would be hundreds, if not thousands of lines of code. And we have done it in 13 lines, and that's formatted. If we wanted to really squish it down, we could have this be like 5 or 6. So this is something that is, for me, having done so much of this in Go and seeing what is done in other languages, is really, really powerful and useful because you're often interacting with APIs. Even if it's not Kubernetes, you can have these derives and things that just make writing something for the cloud and interacting with APIs and massaging that data, like I talked about, a very, very simple process. And so we'll go ahead and actually try to run this example in a little bit. I'll see, because right now I think it's under some active construction on the main branch, but it really gives us some power there to do what we need to. And another thing that we find very useful, particularly in the cloud world, that we didn't mention before, is something called features. So I'll show you actually what this looks like. So inside of Kubelet, inside the cargo file that we talked about, that we were showing, that Ryan was showing earlier, you can see that it's declaring the kubelet, it's saying our version, all the different things that are in there. But then you see this feature section, and large libraries generally have this. Now, what this does is allows you to selectively import code and turn on and off things you don't need with ease. So the way we use this quite a bit is with the derive feature, but also the CLI feature. So the CLI feature is an optional thing. If you want to build this into your own CLI, we have all the plumbing there to do that. But if you're not using it and you want to use it purely as a library in something else, you can do that without pulling in the heavier dependency of struct_opt, which is a command line flag parser. So basically, we now have this dependency down here that doesn't get imported at all unless you specifically ask for it to be imported. But this also goes into code. And so inside of here, we have this config object. Now, this config thing's a little gnarly. There's a bunch of stuff going on in here. But a lot of different things. Like we're not importing in things unless we need it. So this is just saying, if I have a feature called CLI, please import this code. But this also goes down. I'm going to have to scroll down to get to it. Sorry. The actual struct that does all the parsing. So we're basically not importing an entire struct based on whether or not we enabled a feature. And so right here, you'll see that we have the if we have CLI set, or if we're building our documentation, then we are going to use it. And so these things add on. You can also conditionally build parts of your code depending on your operating system. All these things are very, very useful when you have something that you want to run on any system anywhere and only import exactly what it needs. So when you build the stuff for your Windows code, or for Mac OS, if there's some, like in our case where there's a bug we had to work around, then we are able to only pull in those fixes or those hacks when we need them. And so it's really, really powerful. So let's go ahead, and now that I've kind of talked about the code, if anyone wants to see something else or more explanations, feel free to drop questions. But we can look back here and we see that our deployment is complete. So now I can actually go into a normal AKS style workflow. So let's go ahead into a terminal. And here in the terminal, I'm in the Krustlet repository. I'm actually on a branch because I like to live on the edge. And so right here, we're going to go ahead and just first pull down our credentials. If you're not familiar, it is AKS credentials. Actually, here, I'm just going to pull it from the doc so you can see what this looks like. So this is actually in the documentation that I was showing earlier. So if we go into the docs and the how-to and back to that Azure, because as much as I've done AKS, I always have to look up the command again, and then I have to remember my resource group, which is called Krusty. So the name is Krustlet, and I'm going to call, and my resource group is called Krusty. So this will actually go fetch the credentials, put them into your local kube config if you're new to Kubernetes, and it's going to tell me I already have it because I had one before as I was testing this. But now I'm actually talking to that cluster. You can see if I do kubectl cluster info, it's going to return information about the cluster, maybe, if it decides to. There we go. And then we can see that our agent is running against the API. So this Krustlet WASI node is actually going to allow us to run WebAssembly modules inside of Kubernetes, which we're going to show right now, which is really cool. And like I said, you don't have to use this to run WebAssembly modules if that's not your thing. The point of this is to show that we were able to use Rust to build a very powerful Kubernetes application, which is kind of becoming one of the de facto things for running in the cloud in Rust without lots of cruft and extra bloat, and really in a powerful and safe and correct way. And so let's go ahead and show that. So now that we have that node running, I'm going to go ahead and run a few examples. Sorry, wrong one. Let's go ahead and start off with Hello World Rust. So I'm going to go ahead and apply a manifest here. Actually, you know what? I'm going to go ahead and show you what this looks like first here in the terminal. So you'll see here we're creating some configuration. If you're familiar with Kubernetes, then you'll know what this is. I'm not going to go over every object. But here we have a pod, and this pod is the base unit of Kubernetes. It's what runs your thing, whatever it might be. And right here, we're actually pulling down a WebAssembly module from an ACR registry. So you can store WebAssembly modules there, and Helm charts there, and containers there, all sorts of things. And so we're pulling that down, and then we're going to run that WebAssembly module inside of Kubernetes. And this is targeting only specific nodes, ones that run WebAssembly modules. So let's go ahead and do the apply of that manifest. And it was created. So we'll see that it should have run all the way to completion. Yeah, see, so it exited with an exit code of 0 because it was just only doing one thing. But you can interact with this just like you would a normal Kubernetes node. So I can say kube control logs, logs hello world WASI Rust. And you can see that it printed a standard out and standard error. It printed out some environment variables we set, and then also the bacon ipsum, which is our funny version of the lorem ipsum filler text. And so you can see that it printed out all of that information. So basically, like I said, all of this is running in REST. We didn't take any shortcuts. We didn't do anything to like work around this. This is all Rust, and we're able to implement the same APIs that Kubernetes has and be able to pass through and get this kind of information. So there's that. I just want to pause in case anyone has any questions, and then I think we have a little bit more time for one more demo, but let's just stop in case there's any questions that come through on the comments or on Discord. Anything you wanted to add to this, Ryan, while I was talking about it? Anything that I may have missed or glossed over?
It looks great. It looks very simple and really awesome. It's a really cool project.
Okay, well, we're going to attempt is the word, because we have angered the demo gods probably at some point along this. So let's go ahead and go to that example in Crater. So this example is actually really cool because if you're familiar with Kubernetes, this is something that actually takes quite a bit of work normally to set up, and that's why I showed it first. So in the Moose example here, actually is meant to run an admission controller and a whole bunch of other Kubernetes things. So if you're familiar with Kubernetes, you're probably like, "Ooh, that's cool." If you're not, you're like, "What in the world is that?" Don't worry, there's just a lot of things going on here in the background. You can actually see that there's these scripts that will allow you to run like for different Moose that you're creating and all sorts of stuff. So we're gonna go ahead and give it a whirl live. And like I said, this could utterly fail, but why not? We have a little bit of extra time, so I'll go ahead and share that. So I believe the instructions you can follow are out here, or maybe not. If not, then we're going to be trying to do it from memory, which is always fun. So we're going to go ahead and start right here by running because we're running the Krustlet node already, we can go ahead and try to run this. So we're going to go into Crater. And the nice thing about Cargo is you can do cargo run example, and then give it an example, which in this case is Moose. And we'll see if it runs for us. So this is going to run basically a whole Kubernetes operator. And while this might have to build for a second. So while that's building, you'll see here that we have all these different things that are being implemented, which I'm not going to go into, but it's actually implementing a full state machine to handle each part of the Moose's life cycle. And there's some funny things in here that we'll see, like the sounds that the Moose makes and if it's munching or roaming. So we have a state called roam. But all of these things are fairly easy to write. So this is a whole like fully featured if kind of contrived controller in, let me check, I think it's 400 lines. Yeah, 413 lines that does all this. So it's if you've ever written a controller in Kubernetes before, generally it's a lot more work than a controller for Kubernetes is normally a lot more work than this. So let's see if it ran. Oh, oops, I forgot to add features. Yeah, like I said, it decided it had to compile. So we'll see. Oh, good. It's faster than I thought. Okay, so this might take longer than I thought. So we'll go ahead and just stop it there. I don't want to take too much time because Rust builds, because you're doing all of that checking to make sure you're not misusing your data and whatnot, it takes a little bit longer to build. So we'll go ahead and stop it there and just kind of tie up here with the end. But like I said, this is just to get people interested and excited in trying it out. It might not be worth it for you to try and do your whole your whole, like everything new in Rust. I mean, maybe you're at that state where you want to try something completely greenfield and new. But we're going to put up some resources here for you to look at. The first one being the Rust Lang book. This is basically the Rust Bible. It's the way that it explains every single part of the Rust language, starting off really easy and then going into exquisite detail about each of the underlying things. It's a very, very good resource. We also have the link to the Rust SDK and the Krustlet site in case you're interested in those things. Were there any other resources you wanted to point out, Ryan, that would be good for people?
No, I think these are the ones to really take a look at.
Okay, sweet. So really, if you have any questions for us, feel free to reach out. We're both available. I mean, Ryan is in Germany, so he is closer to the time zone than I am. But we're both always available to help out, to mentor, to give ideas. And if you're interested in any of these projects we've seen that we've been demoing, please reach out. The SDK, like we said, heavy construction right now. So any feedback from people who are trying it out is great. Same thing with Krustlet. We're actually very close. Our next releases will be our 1.0 alphas. And so having people try it out and tell us, oh, this is great, or to try out new things with what we're doing is also very, very useful for us to have the feedback that we need. So, we had one question coming in here. One was if I would like to build and run a web API in AKS, could you do that with Krustlet? In a sense, yes, you could use Krustlet for inspiration, but also you can use, if you're going to be doing it like very embedded into Kubernetes with the kind of CRD things I mentioned before, you can do that definitely with what's called with Krustlet, with the Crater crate. That one will allow you to build your own controller with it's pretty simple and straightforward. I'm not seeing too many other questions. We'll give it just another second and then probably just tie up. Because it's the internet, we'll have to sit here in awkward silence while we wait for the internet to catch up. And then and then if there's no other questions, we'll go ahead and end. Okay, I'm not seeing anything else come through, so I think we'll go ahead and call it. So thank you, everyone. Really, this was a great experience for us. I have enjoyed, and also, yes, thank you for the last comment that you hadn't heard about Crater. Glad that we could let you know. Feel free to try it out. And really, thank you so much for coming to this. We appreciate all the excitement that comes from events like this and everyone's involvement.
Thank you.